And she has been doing actually a lot of work in the same realm in the sense of making mobility more efficient. She has been working a lot with the parking data. She does a lot of work with the Seattle Department of Transportation. And she has been collaborating with me in also doing some of the efficient mobility work in Nashville. So thank you, Lillian, for coming.
Yeah, okay, so I think some of the things that I'll talk about have already been mentioned to some degree, some of the challenges and opportunities. But nonetheless, I'm going to talk about learning and decision-making and incentives using mobility data, and I'll focus on one particular application. Even though this is a multimodal workshop, I'm going to talk mostly about parking, and I'll focus on 3 case studies there where I think that we can identify some challenges and opportunities for other areas of mobility. So hopefully that comes across when I go through talking. Hopefully don't go too far down the rabbit hole with parking. Okay, so just some motivation. We've already seen some of this, so I'll be quick with it. Obviously, there's lots of new sensors being integrated into cities, whether they're owned by third parties, companies, for example, or by people with their own mobile devices or cities. So with this, we're seeing not only the technology adoption, but the integration into the way that the city operates. And so this is sort of the impetus for this smart cities or smart connected communities concept. And so this really supports and enables data-driven governance, so policies that are adaptive based on the kinds of data that we're collecting and the way in which people are evolving as citizens in cities because of technology adoption. Okay, so one of the things I'd like to point out is that one of the phenomena we're seeing over the last, say, 10 years is this push towards open data. So this is particularly a big deal in Washington. We actually have a requirement by law that any data that's collected by the government has to be made available. So even if it's not put out there, you could do a request for this information, and it has to be given to anybody. It does, not just people who live in Washington. And so other cities have similar open data kinds of policies, or they're pushing to have open data portals, for example, to increase transparency, for example, and accountability and civic engagement. So this is all great. And if you go, for example, to the one for Tennessee, you'll be able to see information on a variety of different things. But this really isn't the solution to everything. So it's great for us researchers to have access to some data, for example. But this really has some challenges, some that I've faced personally from my trying to just use data that you scrape from the web. So first and foremost, the data format is a challenge. So different vendors produce different pieces of equipment. So in the case of parking, there's a variety of different vendors who make smart meters, and they all collect data in different formats, and then cities want to see this in different formats, so that makes it challenging. In addition, there's a lack of domain expertise. So if I just come at this as a data scientist, I have no idea what I'm looking at most of the time if I just pull down some Excel sheet. So I think this really means that, or identifies that this issue of, as researchers or even like people who are citizens of a particular area, if they want to leverage this open data to either understand what's happening in their city or to do research in some capacity, you really need to connect with the domain experts, so the people who are managing and operating these cities. Okay, so with this first point that I made about sensor integration and then also this push for open data, and this has already been pointed out today by Janos, people are really going from being passive participants to active participants, and so the evolution of this process is as follows. So people have started to become, or they started at some point to become aware of technologies. For example, you might have known the guy down the street who had the fancy new iPhone, and then suddenly you had a fancy new iPhone, and everybody had a fancy new iPhone, and you become literate in the way to use this in your everyday life. And then ultimately, sort of where we are now, we're starting to integrate that device into the way that we make decisions in such a way that we're being strategic about the information that we're getting on this device. So this is particularly true in the area of transportation. Alex talked about this just a few minutes ago, and this is true not just for apps like Waze or Google, which might tell you how to drive your personal car, but also for ride-sharing services or transit or even your bicycle. All of these modes together get aggregated in some sense onto your cell phone through third parties, and there's information that's provided to you about how to move through the city based on this. So we sort of see this closed-loop process between the physical system, the sensor layer, the third parties operating in the cloud, and then the decision-making that's happening at the human level, which then implements that decision in the physical layer. Okay, so I'll just point out some research questions that sort of arise as a result of this closed-loop process. Again, some of these we've already heard about. Some of the things that we'd be interested in doing, given that there's this closed-loop process with the human in the loop and that we have more access to data, is to learn plausible models that have theoretical foundations of human behaviors. We already heard that humans are irrational, so I'll talk a bit more about that, or can be irrational to some degree. So I'll talk a bit more about that towards the end of this talk. So we want to do that leveraging data that we currently have. So, and do it in a way that is adaptable to new data sources that may be integrated as we move down the line. So it's one thing to think about the future and all of the nice things that you might have in terms of available data, 10, 15 years from now, but if we want to have real change or we want to have real impact now, we need to think about what sources of data we have currently. And so that'll play a role in the discussion that I'll bring forth regarding parking here shortly. The second is to design data-driven policies that promote efficient use of resources. That's sort of an obvious one. And the last is to really think about how we can utilize new technologies in novel ways to deploy incentives and information together. So I'll talk also about this toward the end of the talk, this importance of coupling the incentive with information. Okay, so as I said, I'm just going to focus on one application. We're going to focus on parking. Everybody's had that experience of driving around in circles and trying to find a spot. It's really annoying. But it's a sort of integral part of your life if you drive your own personal vehicle. So just some motivation. As we all know, parking causes unwanted congestion. This is primarily due to the fact that there's a big price discrepancy between on-street and off-street options. So people are incentivized to sort of look for some amount of time until they get too exhausted and either go to a garage or just give up. So this chart here is, well, it came out of the Seattle Times. It's produced by INRIX, so a company that does transportation studies. So that's why Seattle's highlighted. But I think the interesting thing to see here is that there's, well, one, Nashville's not in the list yet, so maybe you guys will be there soon. But there's 10 cities here, and they have a handful of different metrics. So search time in minutes per trip, annual search time, so hours per driver per year, and then average 2-hour parking cost, 1 mile, within 1 mile of the city center. And so some of these costs are fairly high. In New York, it's $33 to park for 2 hours. That's pretty significant. So you can see that there's significant costs in terms of both time wasted as well as monetary costs due to people searching for parking. Okay, so I'll just give you a sort of perspective on how cities currently combat these issues. A lot of this is done based on heuristics. A lot of those policies are beginning to change now as more data is available. But the traditional way in which parking prices and other policies are set in cities is that they first establish a target occupancy. This is usually 60 to 80%. The idea being that if it's 60 to 80% full, if a person arrives at that block face, they can find a spot. But at the same time, you're maximizing utilization in some sense. But this is generally applied uniformly to all the blocks, either in a city or in a broad neighborhood. There's no distinction based on the features of that neighborhood. These prices are also and other policies tend to be set based on annual studies where people walk around and manually count cars. So I've done this myself in Seattle to see if I could collect some ground truth data. This is extremely exhausting, and the data you get back is not very good at all. I know because I made huge mistakes in just counting cars. You get tired after 8 to 10 hours. You're just like, well, I don't know what I'm counting anymore. And so this makes it really challenging. And then prices tend to be set based on a prescribed schedule. using the data based on this annual study, which is often one time a year the count is done. This is particularly, I'm speaking largely in terms of Seattle, so I assume that other cities are similar in the way that they do their studies and price setting. So the question we're sort of going to ask is whether or not we can do this in a smarter way, leveraging new data sources. And so this is really what Seattle's doing now. So they're moving away from this old traditional model into something that where they can leverage the new data streams they have. So in Seattle, for example, they've replaced all the meters with smart meters. I think Nashville is moving in that direction as well. They also have a pay-by-phone system. So that pay-by-phone is in a lot of cities. So they basically allow you to pay using your phone instead of having to get out and use the meter itself. You can also re-update your time, so it's got a lot of nice features. It gives you information about things, which I'll talk about later too. So yeah, the question we're asking is why can't we, or why not use the data in a smarter way now that we have it in higher frequency and volume. So then, if that's so easy, then why isn't it done? So there's a handful of challenges that I'd like to draw your attention to. First, cities only have a handful of knobs that they can turn, so they can adjust the price, but there's rules about how much you can adjust the price. Usually there's a maximum cap on the per hour amount. There are rules regarding disabled placard holders and government vehicles, or car sharing companies. So Reach Now is the BMW one, Car2Go. Companies like this usually pay a flat fee for the year, and their customers can just park wherever. So they do the floating system as opposed to like Zipcar, where you have a designated zone to park in. In addition, as we saw in Alex's talk, humans are fickle and they tend to be less than rational. And there's many empirical studies that show that, for example, price is not the only factor in the decision you make. In fact, location is the primary factor, and then information also plays a big role. And this is really true of a lot of policy design and operations decisions for cities, not just parking. So, so I think that what I wanted to highlight is some of the challenges in parking, but then for you guys to think, and maybe later during the panel for us to discuss how some of these things arise in other areas. Okay, so let's consider some successes and failures. Specifically, we'll look at examples of experiments that were only focusing on price. So two that you may have heard of, these were done, actually now it's been several years. So it's, SF Park was 2011 to 2013, and I think LA Express Park started in 2012. These are, they had pilot studies during those years, and they're ongoing efforts in both these cities. So basically, so in San Francisco and LA, basically what they did is they said, okay, well, we want to alleviate some of the issues related to parking, so congestion, as well as decrease congestion while increasing utilization. And so how it works is the following. They both are focusing primarily on price as a means to alleviate parking-related congestion. They installed different technologies, including smart meters, which were already being put in place. They also installed occupancy meters. If you're going to do a formal study, you need to have some ground truth so that you can make sure that what your whatever pricing or models you're building are validated in some sense. They opened up the payment options to mobile apps, cash, and credit card options. The idea was to come up with dynamic parking rates based on not only demand, but time of day and the length of stay. And to do this so now these things, currently most parking policy is set in a static fashion, but based on these features, the way they wanted to do it is in more of a dynamic setting. They also thought about the information problem, but as I'll point out, not completely. So LA uses both dynamic message signs and mobile apps. San Francisco just used the mobile app. And they also had a management system in place. So they, if you're going to collect all this data and then make decisions, you need somewhere to store the data, process the data. You need people who can develop analytics based on that data and then make decisions based on that data. Okay, so just to give you a kind of overview of the two things, or some historical points about them. So LA started in 2012, as I mentioned, in a small area in, relatively small in the downtown part of LA, so 4.5 square miles. It's since expanded because of its success. And it was initially a one-year pilot, and I think this is an important point. Both of these projects were funded by US DOT or other federal funds, roughly at an 80 to 20% ratio, so 80% from at the federal level and then 20% of city funds. So the cost is not, it's not free, right? To install the sensor technology and make sure that it's sustainable, there's certainly some cost associated with that. San Francisco had a similar setup. Instead of focusing on one central area, though, they decided to break it into the different neighborhoods. San Francisco. San Francisco has a lot of different neighborhoods with different features. So they chose, 7,000 of their 28,000 metered spaces, and then 12,000 of the spaces in their 15 to 20 city-owned garages. Again, they're also federally funded at about the same rate. So here's just to point out some successes and failures. I would say that they're both a success in the fact that they caused an increase in utilization while they had a drop in price on average. I think in the LA case, it was $1.96 on average for parking on street per hour, and it went down to like $1.76. They also saw a decrease in congestion. But some of the issues that came up are that they had limited funding. So in terms of sustainability, that was an issue. So San Francisco decommissioned all of their sensors. It's too much to be able to collect that data and store it. LA, on the other hand, somehow they've been able to manage to continue to fund this, and they're expanding it and installing more sensors. So it'd be interesting to find out exactly how they're doing that. Both of them saw, and more so in San Francisco, saw significant public pushback. So in San Francisco, for example, there was a lot of neighborhoods where they wanted to do these studies, but the people who lived there didn't want to have these meters in their, in their backyard for whatever reason. I don't know. There's just more pushback from the public that they had to deal with. Users lacked information on pricing changes. So in San Francisco, the first they did two studies. The first study had limited success, and they found that by advertising the pricing changes in the app, they had an increase in the response rate to the price changes. What else is good to point out? Oh, they both have issues with non-paying users, so it's one thing to change prices, but when you have a significant number of disabled placard holders and TNCs who are using spaces illegally, or government vehicles who don't pay, then that sort of decreases the amount of change that you can affect. Price elasticity was found to be limited. So with these, basically I guess the two key issues besides the funding is that both had serious issues with information dissemination and price elasticity, the fact that the price elasticity was limited. Okay, so I'll talk about the third sort of case study. This one is work that we're doing at UW. So here we think about a case in which we're going to couple incentives together with information and location, so not just focusing only on price. So just to give you the sort of view of Seattle, it's slightly different. We don't have the technology there to do rapid price changes, and there's no money to put those in place. Where the city has not been able to procure such a federal grant as LA and San Francisco. So the way that they set prices, as I mentioned earlier, so they do these manual studies, they set a target occupancy rate, they break the city into zones, and they set a prescribed schedule yearly and then adjust. So in Seattle, the neighborhood boundaries are just predetermined based on almost arbitrarily. I mean, they're sort of like learned neighborhood boundaries that have developed over time, but it has nothing to do with parking. They're not set at all based on the way in which people use the on-street parking or off-street options in those zones. Prices are quasi-static, so they have time-of-day pricing, but it's just fixed for the year, and then they revise it based on this manual study. And so what we're trying to do in Seattle is take the data that we do have available, which is paid transactions, that's it. We don't have any ground truth other than some small studies that we've been doing to validate our models, but not at a citywide level. And we have a sense of what, using GIS data, we have a sense of what where the blocks are and neighborhood boundaries and what the neighborhood characteristics are. Okay, so we'll focus on one area in Seattle that is sort of a nice area to study because it's extremely dense. It has the most coverage of on-street parking blocks, and then it's highly mixed use. So residential, commercial, there's tourist attractions in there, there's all kinds of places to go eat. It's a really interesting mixed-use neighborhood. Okay, so just we use off-the-shelf tools, nothing special here. This is literally just a tool that you would learn in your first year machine learning class or statistics class maybe even. So we take some of the data that we have, and I'll tell you which are the features we use. And we want to ask how similar are occupancy profiles across the city or across the particular zone we're looking in, Belltown in this case, and how many zones should we break it into? What is the best way to do that? So as an example, suppose you have a block that on average has 85% occupancy at 6 p.m. on Fridays. What other blocks look similar? Yeah, so the features that we feed into this model that will sort of break apart the different blocks into different groups are the most simple things you can think of. So something that has to do with space, and which is the longitude and latitude, and then something that has to do with the actual utilization, so occupancy. So this was done on a set of data between 2016 and 2017. Currently the way that Belltown is divided is, again, arbitrarily. There's a street, I think it's Pine Street, they just drew a line and said, okay, everything south of here gets one price, everything north of here gets one price. And so our model suggests that this area should be broken into 4 zones. And so the zones are indicated by the colored dots, if you can see them. And then the circles sort of say how it spatially varies. And so what's interesting about these zones is the following. So we didn't put any of this information into the data that we use, but the bottom area is where all the bars are. And so you see at 6 p.m. on Friday, all of those get grouped together. That's what that pink color is. The cyan color area, so the one in the center, is where everybody lives. So that's a highly residential zone. The blue, a dark blue one on the top abuts an area that has lots of tourist attractions. So Chihuly Museum, Science Center is there, the Needle is there, all that stuff. And the light green area is where all of the cruise ships come in. So somehow it naturally comes out of the data that the way in which parking is occurring is most similar in these zones, and the reasoning, there's a nice interpretation of why that is the case, based on the neighborhood features. So you might ask whether or not this is consistent, does this vary in time? And it turns out that basically every weekday has similar structure, and the Saturday has different structure. Sunday, nobody gets charged for parking, so we don't have any data on that. Each weekday gets broken into 2 periods in which you have almost exactly the same division of this area. So this is basically validating that having quasi-static pricing schemes is probably a reasonable approach. So 8 to 3 is good, 3 to 8 is good. The way that Seattle currently does it is in 3 chunks, so morning, evening, or morning, afternoon, evening. So this suggests perhaps a better partitioning of the time. Another question you might ask is whether or not price is driving the shape of this, because obviously there's some price set there. So we looked at pricing changes from 2016 to 2017 for 1 month to check whether or not the model is consistent across pricing changes, and it turns out that it is fairly consistent. These 2 pictures show the 2016 $1.50 an hour price compared to the 2017 $1 an hour price. And essentially, you get the same clustering. However, you have the top plot shows that there is a fairly significant change, both increase and decrease, from year to year in the occupancy patterns. So there was, that shows, on average, the increase and decrease. Okay, so basically what this is showing is that we can take data that we do have, which is not that hard to get. As we get more and more smart meters in cities, you can just take this one set of information and do some interesting analysis that can help you set policies in a smarter way without spending a lot of money. So one question you might ask is, how can the city actually use this? Well, They can use it to rezone based on this partition we're suggesting. They can set prices within these new zones. And this is something Seattle is going to explore with us in the Pike Pine area, which is a specific region, a neighborhood in Seattle. And so just sort of in summary, what we've shown so far is that if known by people, the price can be effective. So that's sort of what the SF Park and LA Express Park show. But since location drives people's parking choice, there's certainly smarter ways to partition the city. So one of the things we're doing now is targeting information to increase price change awareness and couple that with incentives to ensure that you have more effective pricing, or more effective or more efficient pricing. Parking. Okay, so in order to do that, to target these information and incentives together, we want to take into consideration salient features of the way that humans make decisions, and we already heard that they can be less than rational, and this is a particular example that shows sort of a characteristic of their decision making. So in particular, we tend to be loss averse and risk sensitive, and we treat losses and gains very differently. So this is a plot of from 2015 of some Uber data when they used to do surge pricing. I think now they under the hood do it, but don't call it that. So there was a concert let out in this period from 10:30 to 12. So there was this, the red dots show how many people are opening the app, and so you see a swing that goes up. Surge price goes into effect based on Uber's algorithm. So at the same time, you see a slight increase in the number of drivers, which is green. But then as the surge price takes effect, there's a significant drop-off in the number of passengers that are opening the app. And there's only a slight increase in the green color. So what this says is that passengers see the cost as a major loss, whereas drivers see the increase in the money they can make as a marginal gain. Okay, the other thing that's interesting about humans is that they compare things to reference points. So in particular, you might think about the status quo or what happened to you in the past in your decision making. I commonly do this. And so people classify whether something is a gain or a loss relative to a reference point. So you might ask, how long did it take me to find parking yesterday? In addition, the perceived value of a change in probability depends on the reference point. So you might compare this concept or this potential event of finding a parking spot going from complete impossibility to slight possibility, so 0 to 10%, let's say. That's going to be perceived as way more valuable than if it just went from 45% chance to 55% chance. So that small increase at a higher rate is less valuable than at a lower, from going from impossibility to possibility. Okay, so we want to incorporate these things into a model for which we can design information coupled with incentives. And so the idea with the parking system, or the way that we're going to do this in the parking case, is we're going to take this abstract view, and so this person designing the incentives coupled with information, the observation that they get is the sort of aggregate occupancy for a collection of blocks, or even at the block face level. You don't have any information about the individual's choice. The user, the parker, gets some information through dynamic message signs or cell phone apps, as we saw in the LA Express Park case. We assume that their reference point is drawn from some distribution, and we want to shape this distribution ultimately. Then the incentive affects the model, so we can't treat the reference point as fixed in time. It's going to be affected by the incentive. And then a decision is made. So I shift your reference point, a decision is made, and then you choose where to park. And sort of this repeats in a closed loop fashion. Okay, so to give you an example scenario of sort of what the information or the incentive might be. The reference point might be a weighted combination of how long it takes you to find parking plus the last price you paid. These things are unknown to the incentive designer. The incentive will be a discount to a local business, as an example, for parking at designated blocks. And I'll tell you about the specific thing we're doing in Seattle to test this. And you have a mechanism to validate. So if you have a cell phone app where you record where you park, then you can walk into the business, show that's where you parked, and they can offer you the incentive. So there's no money coming out of the pocket of the city to do this. It's just local businesses that are coming together to ensure that they are getting more, that the vitality of a particular business district is increased, and it's better for the people who live there, right? And the observable, again, is this occupancy distribution across a neighborhood. All right, so how do we solve this? This is sort of the technical approach. So the typical way to solve these kinds of problems, because you have unknown information about this underlying parameter, the reference point, you also have unknown information about, or you're getting a random sample of what the occupancy looks like over time. So you can think about this as going to a casino and you have a bunch of slot machines, you're trying to figure out which one to pool, so I'm trying to decide which incentive to offer that gives me the best reward, given all this randomness in the system. So this is called a multi-arm bandit problem, and essentially what you do is you design an algorithm that allows you to explore and exploit the information that you're getting by repeatedly pulling these arms. Okay, so in the context of the parking, the arms are the different incentives. So for example, you might have different discount levels at local businesses. You might have a lottery mechanism, as Alex suggested. There's a variety of things that you could do. We're actually trying this in experiments. We're doing this discounts at local businesses. The reward is going to be a function of this reference point that's unknown a priori. It may even be unknown to the user themselves. There's a cost of offering the incentive. And there's effectiveness at distributing parking, as observed through the parking transactions, which, again, are somewhat noisy. So we metrize this performance in the classic way that you do this. So we have a regret. So we compare, at least in the theoretical context or analysis of the algorithm, you compare the what would happen if you actually knew the best reward to offer to whatever it is that your algorithm is doing. So this is exactly what the word regret means. You just sort of measure your regret after you affect the or pull the incentive. Okay, so of course there's the usual kinds of theoretical guarantees that you can get, but basically we can prove in a theoretical sense that our algorithm will eventually identify in an asymptotic sense the best incentive that offers or to offer that will redistribute parking. So this is the theory part. What does this mean for practice? So as I mentioned or alluded to several times, we're in this spring we're creating experiments in the U District area. So there's something called the U District the U District Partnership, which is a collection of businesses. They're a business improvement area. And so we're working with them to offer discounts at all of the businesses in this U District area, which includes a number of coffee shops, a number of restaurants, bookshops, all that kind of stuff. And it's more than just students who live there. It's actually a pretty diverse neighborhood. And it's also a good place to study because they're opening a new light rail station in, I think, 2021, so soon, either 2020 or 2021. So doing this adjustment of behavior prior to the opening of that will be interesting to see what are the long-term effects, especially as new features are entering into the system. So the idea is to couple these, so target information on the app, so this pay-by-phone app that people can use to pay for their parking, with an incentive like a discount to a local business in order to shift people from high-demand areas to areas that see limited utilization. So we're testing that again this spring, so I hope to have some results the next time I get to report to you guys to say that we actually have some success. So I'll just sort of summarize what I've shown you. So in these three cases, I highlighted a couple challenges regarding policy design for these resource-constrained systems, particularly when they have humans in the loop. We focused on parking, but I think a lot of these features and challenges we discussed are important for other systems. When humans are involved, the design features should be broader than money. It's not just always about money. And the question that we should ask ourselves are, what are those features? And that may depend on the application. In parking, it turned out to be location and the information that you have access to. There are still limitations in the technologies and policy constraints. So specifically, it's nice to say, oh, we have these smart cities with all of these sensors everywhere, but when you go to actually try to implement things or work with the cities as they are now, those technologies don't provide you the whole picture. There's, again, these like data format challenges, domain expertise. There's data storage issues. Like when I first worked with Seattle, they didn't even know how to give me the data, so they mailed it to me on a CD. Now it's since changed. They have a database, but a few years ago, this was 2015. So I think it's interesting that, especially as a technologist or researcher, we think, oh, well, everybody's, at the same place that we are at a university where we have access to all of this, places to store data and places to run algorithms. Well, it's not always the case that cities are at that point yet. So we need to take that into consideration when we collaborate. And we also need to do it in a way that makes sure that it's generalizable when those technologies become available. Another thing that we pointed out is that information needs to be coupled with incentives, is largely because humans are involved, and they make their decisions not just based on utility maximization, but rather on a variety of factors having to do with information they have access to. Funding is an issue, and city resources, so it's not, a lot of the money that comes is through a tax base, and that's not always a huge pot, at least in my understanding. And so there's questions about whether or not this should be outsourced. So one of the things that Seattle's discussing, for example, is whether or not they should hire a third party to manage all of their data and push it out into not into the public domain, but into some other private party's ownership. And so that brings forth issues of privacy and, data ownership in this case, which is challenging. And then, of course, there's maintenance and stability along with that. Who is going to maintain these servers? Who's going to maintain privacy if you do have some policies in place? And how are you going to ensure that you have money to pay for, to make sure that you can sustain whatever you've invested in? And so, while we focused on this parking case, I think the challenges remain. There's a number of challenges that remain. So while we showed some solutions, there's certainly some issues still there. And this is certainly going to be more complex when we have more modes into consideration. So when we're not talking about a single occupancy vehicle finding a place to park, but rather whether or not you will drive your single occupancy vehicle and park versus taking the bus or some other mode. Okay, so just some final thoughts, and I'll end with this. These are perhaps some under-considered challenges. So a lot of people are thinking about engineering systems design for the future, which is great, right? That appeals to my personal like of science fiction. However, I think there's a lot of basic infrastructure and policy concerns that will impact those designs ultimately that can be considered now. So this is an example of something that's happening for sure in Seattle, and I'm sure elsewhere. So obviously this last mile problem that was discussed, but a big issue is that there they want to subsidize companies like Lyft or Uber to help support the last mile problem. But many of those companies can't comply with the American Disabilities Act. So they can't offer rides to disabled customers. And so then if you can't do that, then you really can't get a government subsidy. So there's some policy constraints that really affect what can be done with new technologies. Again, I mentioned the data issue. Where's the money come from? Where's it going to be stored? How is this going to be sustainable? What to store. Lots of information is collected, so what can we forget and what can we store? And then I think another primary issue is workforce recruiting and development. If cities do not already need, they will certainly need data scientists. And if data scientists being hired by cities can't be paid at the same rate they can be paid at Google, then what do we do about that? How do we ensure that we're getting good people on the workforce to do the things that we need them to do from a data science perspective? And then certainly you need the data scientists to be well-trained in both the domain as well as the data science itself. Okay, so hopefully I didn't go over. I have no idea how long I went. Thanks.
So I'd like to thank Lillian, and if there are some questions for her.
Thanks for that. I'd like to kind of push a little farther on your observation about looking beyond just price signals for incentives, because there's kind of, do you look at things like in the behavioral science theory of planned behavior and value belief norm theory, which say that when you're trying to get people to change their behavior, you want to target the incentive to the biggest obstacles to doing the desired thing. And so financial things work best if the person's having a hard time affording to do the right thing, but otherwise other incentives might be more effective. And are you looking in those directions?
Yeah, so certainly. So we have, working with the eScience Institute at UW, there is a group of sociologists working on looking at demographics in Seattle and trying to understand some of these boundaries to mobility. So, I mean, we're just starting the conversation, but certainly we're thinking about these things. I think that you're absolutely right. It's not, you know, I think that some of these, the demographics of the population and socioeconomic factors are going to be a big deal in the kinds of incentives we can offer.
So what I would suggest is that we break for lunch, and I think the lunch is there. We grab it, and then we can actually keep having a discussion with it.